things, so that was good. Okay, so... Oh, isn't it Kimberly? I mean, wow, I've played that way too many times. Okay, cool. So, what do we notice? Yeah, Fire Emblem. Okay, video game discussion to be continued at 5:30. So, back to chemistry now. Let's take a look at what's happening here. We see that copper... Did I say I was going to give you another one of these before we moved on to redox chemistry? I don't remember. Okay, then let's do another one. Okay, so let's go ahead and let's do another one that we have also done before. Let's see. And that's going to make, of course... Alrighty, so let's go ahead and do the net ionic equation for this. So that is our molecular equation, the normal ones we're used to seeing. Oh, look who's here. Oh, goodness gracious. We have been graced with Gumbo. A visit from Gumbo is always a nice thing, so we are lucky today. What's that? You can't see anything? Is anybody else having this problem? Alright, Rob, you crazy. Okay. Oh dear, the creature has gotten up and he's waddling out of the room now. Okay, we're safe, everyone. So, let's see. If we go ahead and look at this, we can see that we have 2 sodiums plus 2 bromides. And there goes that. Can you hear the creature grumbling, by the way? He might be pretty far away by now, but come on, computer, back to your connection. Alright, we'll just do it this way. No. Let's see. Come on, tablet, you can do it. There we go. Okay. You want to challenge hard mode? Look on my streaming of myself. Yeah, that's going to be very meta. Okay, so that turns into 2 sodiums plus 2 chlorides plus bromine, rather. Okay, so we look now, what's the same on both sides? Sodium. Right, so sodium is the only thing that's completely identical on both sides, so we can get rid of it. What we're left with is 2 bromides plus chlorine gas turns into 2 chlorides plus liquid bromine. Alrighty, so that is our net ionic equation. Alrighty, let's see here. Elsa's got a question, maybe? By the way, I did get your emails as well as one from, maybe it was Shelby or Zoe, I don't remember. But I got your emails, by the way. Something about like videos not working or something on the textbook. Okay, Elsa, did you have a question? Or this reminded me as you were typing. So okay, cool. So let's take a look at what's happening here. We see that we have bromine going from bromide to bromine. I can put the 2 there. And we have chlorine going from elemental chlorine into chloride ions. If we look here, what is the charge of bromide? Not a trick question. -1, right? And what is the charge of bromine, Br2? What's its charge? Let's see. Is it? Do you see a negative up there? No charge. Yeah, it's 0. Yeah, that one was the trick, I guess. Okay, so if we look at chlorine now, Cl2, what's the charge of that? 0, exactly. And as you've already figured out, Elsa, we are moving to -1. So, who remembers from, I don't know, chapter 3 or 4 or something, how do we change the charge of an element? What do we have to mess with? Yeah, exactly. It's all about electrons. So from going from -1 to 0, is that going to be gaining or losing electrons? Okay, so we need Zoe to do our tiebreaker. Oh no, Zoe has joined the wrong side. Okay, think about it. That's okay. That's okay. Yes. No, Rob. Samvel's got the right answer. And Elsa's got it too. Yeah, this is going to be losing electrons. So it's less negative. Remember, the more negative things you have, the more negative you are. So if you get rid of negative things, lose them, you become more positive. All right, how about... hopefully that makes sense. Exactly, whatever you think it is, it's the opposite. So, from going to 0 to -1, what has happened there? Hi, Kaz. Yay, you all win. Gaining electrons. So this is losing electrons, this one's gaining electrons. And so we've also noticed that these two processes are happening at the same time. One thing is losing electrons, and the other thing is gaining electrons. All right, and we actually have fun names for these things. We're going to call this top one oxidation. And that's going to be, yes, if there's no charge, it's 0. That's what a compound is defined as. And we're going to have another word, which is called reduction, which is gaining electrons. Alrighty, and so we have a fun mnemonic here to remember which one is which. If we look at this, we get the Americans' most favorite thing, which is, of course, the oil rig, right? So, oxidation is losing electrons. Oil, oxidation, is losing. Reduction is gaining. Oil rig. Okay, so that's how we can remember this. If you want to see, I know that the names are kind of silly, but if you think about this one that's gaining electrons, its number is reducing, right? It's going down. It went from 0 to -1. That is a reduction, right? That may be also one way to remember this. Okay? So, if we look at this process, we're going to refer to that first one as oxidation, and this one as reduction. Okay, so these processes always have to happen simultaneously. While we're not going to be learning acid-base chemistry this semester, Acid-base is all about protons moving between different compounds. With these reactions, these are all about electrons moving in between different compounds. So in this case, we're moving electrons from bromide onto chlorine. And as a result, bromide is losing electrons, and chlorine is going to gain them. Okay, yes. It gets worse, Zoe, but we're going to just stick with this part right now. Okay, let's go back up to that previous one we had. We had copper plus 2 silver ions turns into 2 silver plus the copper 2 ion. If we want to think about this, which one is being oxidized and which one is being reduced? So we want to think about it. We want to see, okay, what's happening with copper and what's happening with silver. So copper, what's it starting as? Starting at 0 and is going to become 2 plus, right? Or plus 2, yeah. And that's going to be oxidation, right? All right, since we are going up, we are becoming more positive. We're getting rid of electrons. We're losing electrons. That's oil. Oxidation is losing electrons. Conversely, silver is going from plus 1 to 0, which is going to be reduction. See, that one's a little easier to remember because reduction, the number's going down. It's getting reduced. Okay, in this case, it doesn't matter that we have 0 to 2 and plus 1 to 0, because if we look at the balancing, yes, oxidation is gaining electrons. That's a process. So whenever something is gaining electrons, it's being oxidized. Okay, and whenever anything is losing electrons, that's oxidation. I hope that's what I said. Oxidation is losing oil. And reduction is the one that's gaining. Okay, rig. So that's what we'll remember. Okay? Oxidation is losing. Okay? So I'll just write that in parentheses. Losing, and this one's gaining. Okay? Let's see what Zoe's got to say. She got shy. Okay. So, we have been able to see this now with ionic compounds. And so we're going to actually learn a method for kind of accounting for our electrons for things that are not ionic. Oh no. Okay. Oh well. Lag sucks. Oh well. It's frozen. Oh no. Oh, I do see that. Yeah, it says my stream is disconnected. So hopefully now it says it's running again. Are we good? And now it's disconnected, or are we? Okay, I'll just restart. Okay. Okay, hopefully that'll be working now. Share the screen. Okay, go ahead and join in the stream. Let's see what's happening here. I'm moving around. Can you see me? Yay, okay, good. So, in this case, let's go ahead and look at some other examples. So we're going to have some rules to follow when we're talking about accounting for electrons. And so this will allow us, when we have an oxidation or reduction reaction happening, we're going to be able to see what's being oxidized, what's being reduced. All right, we're going to have a couple of rules, okay? So the first rule is anything by itself has what's called an oxidation number equal to 0. So that could be aluminum, or copper, or oxygen, or sulfur, whatever any of these things is. If they're an element by themselves, as in no other elements are involved, your oxidation number will be 0. We saw that up here where the copper that was solid had an oxidation number of 0. And the silver that was solid also had an oxidation number of 0. Same thing with the bromine and chlorine up on this reaction. Okay, so anything that's by itself, its number will always equal 0. Okay, we also know for all simple, that means monoatomic, ions, the oxidation number equals the charge. So, for sodium, that's 1. That's S8, Zoe. Sulfur often exists as a ring of 8 sulfurs. Just in nature, it's just the way that it happens. So, but doesn't matter. The point is anything that's by itself. Doesn't matter how many of them there are. If it's by itself, its oxidation number is 0. Okay? Whatever. Okay, so simple ions. The oxidation number is equal to the charge. Okay, so again, nothing new here. Okay. Third rule is all oxidation numbers in a compound add up to 0. If this is actually just another way of saying charge balancing. For example, if we have CaCl2, we know that this one is plus 2. This one is 2 times minus 1. And all that together adds up to 0. So each chloride being -1 plus our calcium being plus 2, we add those up together, we should get 0. Okay, so this is just another way of talking about charge balancing. Okay, any questions on those first 3? None of these should be necessarily new to us. Anything by itself, 0. Anything that's a simple ion is equal to its charge. And we always have to make sure that our compounds are going to be charge balanced. Okay, we're going to see in molecular compounds, we're going to be doing a similar process. Alrighty, no questions on that so far. So, what we're going to deal with now is, if we look at rule number 3, for molecular compounds, there's just going to be a few things that we're going to have to remember. In molecular compounds, in this order, the oxidation numbers are: fluorine is -1, hydrogen is +1, oxygen is -2, nitrogen is -3, and then we have, continuing on, chlorine is -1, bromine is -1, iodine is -1, and so on. That's more information than you're gonna need. So this last one may be familiar to us, right? These are all the preferred charges of these particular elements. Fluorine prefers a -1 charge, oxygen prefers a -2 charge. We're going to see that in molecular compounds which don't have charges, the oxidation numbers are going to kind of take their place. So, for example, in H2O, this is a molecular compound, right? It is made of nonmetals. We're going to see that in this case, hydrogen's oxidation number is +1 and oxygen's is -2. How did we get that? Well, let me just fix this so it's a little bit clearer. These rules that I've put up here must be followed in order. Okay, so rule number 1 takes precedence, then rule number 2, then rule number 3, then rule number 4. Okay, so you must always obey them in order. If there's ever a discrepancy, the one that's higher up wins. Okay, so rule number 1 will always beat rule number 4. Okay, for example. So, technically, this is not by itself, so rule 1 does not apply. This is not made of simple ions, this is a molecular compound. Aha, so we must know that this is a compound, so its oxidation numbers have to equal 0 when we add them all up together. Okay, so we know rule 3 is going to apply. And then we must follow rule 4. So it says fluorine is -1, and hydrogen is +1, and oxygen blah blah blah. So we must follow it in that order, so there's no fluorine in this molecule, so who cares? We know that hydrogen has to be +1. That's what this rule is saying. And so, if we designate hydrogen as +1, we know that the whole thing has to equal 0. So we know that 2 hydrogens plus 1 oxygen must equal 0. And since hydrogen is +1, I'm going to just make these zeros a little bit more obvious, that oxygen must equal -2. And this is just totally normal. Oxygen likes to be -2, nothing crazy here. However, if we took a look at something a little bit more complex, say SO3, we can figure out what the oxidation numbers of sulfur and oxygen are. So if we look, SO3, is this an element by itself? Do you see SO on the periodic table? No, it's sulfur and oxygen, 2 different elements. So rule number 1 does not apply. Do we have any simple ions here? No, this is a molecular compound. So again, we're going to have to make sure everything adds up to 0. So we know that sulfur plus 3 oxygens must equal 0. And so now we look at rule 4, and we're going to go in that order until we find an element that we have. So fluorine's not here, hydrogen's not here, aha, but oxygen is here. So it tells us oxygen wants to be -2. So let's make it -2. So we're going to plug in -2 for oxygen. And as a result, we're going to see sulfur is going to be +6. Alright, sulfur does not normally take a charge of +6, right? But this is not an ionic compound. These are oxidation numbers. These are just ways for us to keep track of where the electrons are. So, because Samville, if we were to do this, 3 times -2 is -6, right? And so as a result, the algebra, yeah. Okay. Tricky. So again, we're just kind of using these to establish kind of where the electrons are in this molecule. So in this case, the sulfur is electron deficient. The oxygens are kind of withholding electrons from sulfur, right? And we know that because oxygen is more electronegative. Let's make this one more step more complicated. Sodium perchlorate. Yikes. Okay. So, looking at this, is this an element by itself? No, of course we have 3 elements here. Are there any simple ions part of this? In this case, yes, we have a simple ion. Since this is an ionic compound, this guy is a simple ion. So, we know that sodium must be +1. Sodium always takes that charge, right? It's always +1. So the same thing is going to happen here. All right, and so we know this is also a compound, so we need to take into account that sodium plus chlorine plus 4 oxygens equals to 0. So far, we know that sodium is +1. All right, and so now we're going to go back up to that 4th rule, and we're going to see which elements we have. Again, we're going to follow this order. So fluorine, don't have it. Hydrogen, don't have it. Oxygen, we do have it. So we go ahead and plug in for oxygen. And so now we're able to solve for chlorine. If you were to say, well, wait a second, we have chlorine here likes to be -1. Let's go ahead and plug that in. If you were to do that, you're going to get +1 minus 1 minus 8 equals 0. Mathematically, that does not work. We would violate rule 3. Can't do that. So, we need to basically figure out all but one of our elements. And the last one we're going to solve for algebraically. So, we have 1 plus chlorine minus 8 equals 0. So chlorine minus 7 equals 0. So therefore chlorine is +7. Okay, so in this compound, we would say that sodium is +1, chlorine is +7, and oxygen is -2. So even though there's 4 oxygens, each one of those is going to be -2. So we always report for one atom of that. I know this is fun and exciting, right? Let's see this now in context of a reaction. Okay, so let's take methane. Fun thing, by the way, is in these reactions, you do not need to balance them in order to figure out the oxidation numbers. Don't even worry about balancing. Just do it for each molecule and you'll be okay. So, are there any of these 4 that we know right off the bat? I see a parentheses 2. Yes, oxygen 2. Yeah, right. That's going to be 0, right? Is it -2, Samville? I see oxygen by itself. And remember, anything by itself must be 0. That's our very first rule. Yes. Okay, we have already done water previously. We remember that hydrogen was +1, oxygen was -2. Okay, but these others we have not done yet, so we're going to have to look at them. So, CH4, that's a compound that is not ionic. So, we know that C plus 4 H's must equal 0. Going up, we see that we have a rule for hydrogen. So let's go ahead and do that. No fluorine in this molecule. So C plus 4 equals 0. So C therefore is minus 4. So we're okay with carbon now. And now let's go ahead and do CO2. We see that we have carbon plus 2 oxygens equals 0. No fluorine in this molecule, no hydrogen. Our third one is oxygen. So we know oxygen wants to be negative 2. So in this case, carbon is plus 4. So we would indicate carbon is plus 4, oxygen is minus 2. Did that just completely lose anyone? Are we okay with this? So for any time you have a molecular compound, you're going to have to do this little algebra stuff to figure out the oxidation numbers. Okay, don't see any questions so far. So now let's go ahead and look at this overall reaction. Do we see any elements that have changed oxidation numbers? I know this is a lot of work. It's accounting. So we have to kind of see where the electrons are going in this reaction. So who sees any numbers that have changed? Yeah, oxygen has changed. So if we look, remember we have carbon, hydrogen, oxygen. I'll switch to a different color just so we can see. On the reactant side and product side, these are oxidation numbers, by the way. Went from minus 4 to plus 4. Hydrogen stayed plus 1. And our oxygens, let me move this out of the way, have gone from 0 to negative 2. And carbon also changed, right? So carbon going from negative 4 to plus 4, is that oxidation or reduction? Oxidation. So carbon was oxidized. Great. And what about the reduction? So remember, reduction and oxidation have to happen side by side. You can't have just one of them. H reduced. I see H's are both plus 1 on both sides sample. However, I do agree that oxygen was reduced. Went from 0 to negative 2. Woo, very exciting. So, through this, we were able to use our accounting to figure out which substance or which element was oxidized and which one was reduced. Very fun stuff, I know. Okay, cool. So, let me throw one more curveball at you guys. Zoe is just going to never forgive me for this one. But we got to do it. So, English time. We're going to do an English lesson. So, if I kick a ball, I could say that I kicked a ball. I could also say the ball was kicked by me. Right? Just passive voice. No one would ever say that, but I could, right? What we could say that carbon was oxidized. In the same way, we can say carbon reduced oxygen. Let me write out carbon. And oxygen oxidized carbon. I know you didn't, but here we are. Sig figs, English is all here. You get everything in chemistry. And there we go, we've lost the screen again. Okay, so, come on, Microsoft, just like 3 more days, come on. Okay, so, while carbon was oxidized, it was oxidized by oxygen. Oxygen has taken away the electrons from carbon. All right, and in that process, oxygen gained electrons, right? It took them from carbon, and as a result, it gained them. All right? We call these oxidizing and reducing agents. So if we look back here, we're going to say that O2, oh my goodness, was the oxidizing agent. Oops. It is the component of the reaction which is doing the oxidizing. By contrast, we're going to see that carbon was part of methane before. And so we're going to say that methane was our reducing agent. So just to mess with hungover Zoe, carbon was oxidized, and as a result, it is the reducing agent. It is going to reduce something, and in that process become oxidized. Okay, it's giving electrons away, and as a result, it is losing electrons. Oxygen is going to be gaining electrons, and in that process, it's going to be taking them away from carbon. So it is oxidizing carbon, and in that process, it is becoming reduced. All right, agents must be reactants, and they are the compound in which the oxidized or reduced element is part of. So they have to be compounds. I know that the stupid thing is, I know, this is going to take a little bit of time. So again, I do have practice for you guys, and you'll have plenty of homework to work on this as well. Let's do another reaction, okay? Let's do this one. And let me just reiterate that before I move on. So the agents have to be reactants. Okay, so in this, we know that carbon was oxidized. So we go back to our equation, and we look at which compound was carbon part of that's a reactant. And in that case, it's methane. And so that will be our reducing agent. We then say oxygen was reduced. As a result, it is the oxidizing agent. So we look at, we look at which compound oxygen was part of in the reactants, and that's going to be which our oxidizing agent is going to be. Okay, I know this is just 20,000 new words for you guys, along with all of this accounting. Let's do another example. And we'll go through it together again so we can make this work out. So, okay. Just so you know, all single replacements will always be redox reactions. They will always be oxidation reduction reactions. Double displacements will always be non-redox. Okay, that means that there's no transfer of electrons happening in double displacement, but there's always electron transfer happening in single replacement. Okay, so this is a single replacement reaction. So this one should be easier for us because we have ionic compounds. Those are always easier to do our oxidation numbers. So in zinc iodide, what are our oxidation numbers going to be? Fe is 0. I agree. Zinc is +2. Iodine is -1. That's great. Everyone's doing great so far. Yep, iodine is -1 again. So yeah, with ionic compounds, it's always easier. We don't have to do all that algebra. So we have simple ions. We're happy. We just have rules 1 and 2. And one more. I've got Fe as part of ferrous iodide. Yeah, great. Awesome job, everyone. So let's go ahead and list our reaction components. So zinc has gone from +2 to 0. Iodine has gone from -1 to -1. And iron has gone from 0 to +2. So which of these is oxidized? Remember, oxidation is losing electrons. Great. And yeah, we're going to see that this one gained electrons, and so that one is reduced. All right, and so if we want to think about this, we just have to kind of reverse these, figuring out what our agents are. So the oxidizing agent is always going to be the one that's reduced. So that's going to be zinc, right? Zinc is the one that was reduced. So we look at the reactants part of our equation, and which compound is zinc part of? It's zinc iodide, right? Alrighty, and then we know that since, reducing, I forgot I can erase, hold on. Who's that? Oh, we have a second visit from Gumbo today. We are very lucky. Here he comes. Oh, gosh. There he is again. All happy and licky. Okay. Aha! Remember, your agent must always be a reactant. So our only options are on the left side of the equation. Okay, so in this case, it's just going to be Fe. Okay, that's just by itself. Okay, nothing special happening there. I know, he's like, I hate this. Why am I here? And there he goes, jumped. He almost jumped onto Kaz. That was pretty funny. Okay, remember, agents must be reactants. So in this case, FeI2 is a product, so that cannot be one of our agents. Okay, does that make sense? We're going to do more. I know. I'm sorry, Zoe, but that's how life is. Okay, let's do one more. Alrighty. This is a lot of information, so I agree. But that's why we're going to have our review day at the end, and I'm going to give you plenty of practice so you can kill yourselves over the weekend. So, yeah, fun. Okay. So, next reaction. Yeah, this is not a good day to be hungover. I would not do it Wednesday either. That's going to be another day of lots of math. So, okay, so another reaction. So in this case, we do not have ionic compounds. I've been mean to you guys. So let's go ahead and, oh my gosh, connect our thing to the computer. Two of these should be easy for us because we already have water. We've done that before. Come on, computer. Connect the damn thing. Did you know desktop OF 3HB3C is ready for me to... I can give you guys some other YouTube videos as well. I can refer you. Okay, I'm going to connect it via cable. We'll see if that makes it happier. Okay, it's happy now. So we know already that... Okay. I will have these videos up, and the audio does appear to be working, so that's good. Zoe, I will give homework that will be due next Tuesday. You can definitely start, I think it's homeworks 8 and 9. That's going to cover materials from last week, today, and Wednesday. Okay, so what else do we know about this right away? Oxidation number wise. Yep, 2 homeworks, but it'll be our last 2 homeworks. O2 is 0. Very good. Very good. Now, hydrogen peroxide, this is a little bit tricky, okay? Not an ionic compound, right? This is a molecular compound. If we think about it, we have rules for this, right? 2 H's plus 2 oxygens must equal 0. We have to look at our rules way back where to see that hydrogen is plus 1. That is the first one. So we don't care about oxygen being minus 2. Hydrogen has to be plus 1. So 2 oxygens equals negative 2. Oops. So oxygen in this case is negative 1. Okay, oxygen normally is negative 2, but in this case it's negative 1. Okay, remember for molecular compounds you're going to have to do this little algebra here. And always follow those in order, so fluorine, hydrogen, oxygen, etc. Okay, so what's happening here? Something exciting. Yes, indeed, you're absolutely correct. So in this case, because we have oxygen in 2 components on the product side, we want to look at all of the oxygens involved here. So some of that oxygen has gone to 0, and some has gone to negative 2. So, wait, what am I saying? It was negative 1 to start. Okay, that's the problem. Just thinking that doesn't make any sense. Okay, sorry. Indeed. So, we see oxygen has been both oxidized and reduced. It's gotten both. And Elsa is 100% correct in saying it's the reducing agent. And it's also the oxidizing agent. We only have 1 reactant, so, I mean, that would be the cheating way. Since this is I guess you would still have to do the numbers to see that it's a redox reaction, but since we only have 1 reactant, it's got to be both oxidizing and reducing agent. So, that's your fun thing for today. So this reaction is both the oxidizing agent and the reducing agent. Okay, so oxygen has been oxidized in some cases, and oxygen has been reduced in other cases. So some of the oxygens have given up their electrons to other oxygens, and some have taken them away. So, fun stuff there. Okay, I know we have covered what is quantifiable as 2 metric shit tons of information today. Big day for us. We've done a lot of work. The homeworks will be available, And again, they'll be due the day before the exam so you can look at the answers. This stuff definitely is not the easiest. So I would definitely suggest maybe just every day doing a little bit of practice. Yeah, you guys are doing some of what we're learning on Wednesday, tomorrow. So you're going to be doing a reaction, a simple reaction, and you're going to be working with what's called stoichiometry. So that we're going to learn on Wednesday. Okay? So because of that stupid 1 week that we lost while we were like transitioning, I guess, we're going to be perpetually behind lab, unfortunately. So don't worry, you will learn how to do that. You're going to have 2 homeworks that will be due in 8 days. Experiment 12 or so. So homeworks 8 and 9, hi sweetheart, will be due. So Ingrid, for the last lecture, the one on YouTube, it doesn't have audio for whatever reason, and